All righty, folks. So welcome back. Welcome back. We got one more little section to take a look at here in chapter 4, and it's more integration by substitution. But this time, what if we're using a definite interval? So let's take a look at a function that we've dealt with before here. So say I go like this. Now, if I ask you guys to integrate this, some of you might decide to do this. You might say, you know what? I'm not going to worry about this this U-substitution. I'm just going to multiply it out. Completely valid. Not a bad idea, and probably, honestly, probably what you want to do when it's a small exponent like that. You don't have to, but I mean, you can. So from there, we'd go ahead and we would integrate it. So 4/3 x cubed plus 6x squared minus 9x from 1 to 3. And when you plug all your numbers in there, you get 4/3 times 3 cubed plus 6 times 3 squared plus 9 times 3 minus all these numbers evaluated by 1. So 4/3 cubed plus 6 times 1 squared plus 9 times 1. And if you evaluate it all the way out, you end up getting, you can do that if you want to, or you can trust me that it's going to be 302 over 3 or 102/3. Your call. Call whatever you want. But what about if we were to do a U-sub? Some of you are starting looking and going, hey, I'm a big fan of this U-sub stuff. Some of you definitely are not fans of it yet. Hopefully, eventually, you will feel really comfortable after we've done enough of these. So some of you might be looking and saying, you know what, I'm going to go ahead and do a U-sub. So U is 2x plus 3. So du, you're going to get your differential, 2dx, and then 1/2 du. So you end up going ahead and you're doing your U-sub. Oopsies. Sorry about that. And by the way, what I'm doing right now, just going to tell you right now, it's wrong, okay? And I'll show you why here in a second. So you would go through there and you'd say, all right, well, do my, oops, I forgot my 1/2 there, didn't I? Sorry about that, guys. So 1/2, 1/3 u cubed. Oh my goodness, I have another mistake in there too, don't I? U squared du. And you would end up coming back and you say, all right, well, I got my 1/2. I have my u cubed over 3. And from there, I would go back and then plug it back in. And again, this is what some of you guys would do. I'm not saying you can't do this, although, like I said, there is something that is wrong. We'll talk about that here in a second. And you get back to your actual numbers. And when you plug them all in there, you end up getting your 302 over 3. So you still end up getting the same number. But what you did is you changed the value. So these 1 and 3s, these are the values for when it's x, or the values for when it's in terms of x. But what happens here is they're not the values when it's in terms of u. You know, what I mean by that is this. You got your 2x plus 3. Say I did my u substitution. And I did it all the way out, and I ended up with 1/2. I'm just going to skip a little bit here. U cubed over 3. If these 1 and 3s, these bounds stay the same all the way through, then I should be able to plug it in at any time and still get the same answer. So I should be able to plug them in here, and I'd get 27 over 3 minus 1/3. And friends, this whole problem right here would end up being 13/3. Pretty sure that's not the same thing as 302 over 3. Remember, it's a tad bit off, just a little bit. So if you're a person that wants to go back and go back and use a u substitution, you got to do one of two things. Here's the first thing you can do. You can say, all right, well, I'm going to do a u substitution. I know my bounds are going to change. And so you could come over here and say, and do it like this, and essentially say, I'm keeping the same bounds. And this is considered a valid way to do it. It'd be 100% valid. You can do that, it'd be good, and it would work out pretty darn wonderful. However, if you notice, I'm keep putting this u of 3, u of 1, u of 3, u of 1, u of 3, u of 1. What if we just were to do that? In other words, instead of, once I go to a u sub, what if I actually do my u of 3 and u of 1 and change my bounds? In other words, when I do my u sub, what if I were to just change my bounds when I change to a u? So we still have all the same stuff that we did before. So 2 dx, 1/2 du equals dx. But what if, since my original bounds were 1 and 3, what if I were to change them? So 2 times 1 plus 3. Well, that would become 5. So in place of 1, I would plug in 5, because that's what u of 1 would be. In place of 3, what if I evaluated it into my u function? Well, that would be 9. If we wanted to, we could just evaluate them from the get-go. And by doing that, we end up with something that looks kind of like this. So we have our 1/2. We have our 5. We have our 9. U squared du. So we have u cubed over 3 times 9/5. And if we do it this way, friends, notice what happens here. 9 cubed, that's 729. 9 squared is 81 times another 9 is 729. 5 cubed is 125. So 729 minus 125, well, that would be 604. And again, I would have left my answer as 729 over 3 minus 125 over 3. If this was on the free response, I wouldn't keep going. But to show you what I'm talking about here, especially if this is a multiple choice, notice I end up getting the same answer. When we're doing a u substitution in definite integrals, we have one of two ways we can look at this. Either one is valid. You've got to pick one. If you want to come back and use an expression in terms of x, you have to put u of your bounds all the way through until you get back to it. Or if you want to leave it in terms of u and not have to simplify it later, you can just plug in your numbers into your bounds. Plug your numbers into your bounds to get what those new bounds would be, and then just proceed like normal from there. I'm going to always do it like this right here. So as we go through today and we're evaluating these problems, these are how I'm going to end up solving it. All right, but it's okay if you're a person that likes to do the u of 3, u of 1, u of your lower bound, u of your upper bound. If you want to go back and plug your x expression back in, you can do that. That's okay. Right, nothing wrong with that. I'm just not going to do it. Again, we have a couple of different ways to approach this. So let's try a couple of these here, friends. I'm not going to keep you too terribly long today. You guys have been great sports as we've gone through all this stuff here in Unit 4. So we've learned what this idea of an antiderivative is. So we're going to go through and do some definite integrals with U-substitution. We got one quick little thing that we need to talk about as soon as we're done with this, and that's about even and odd functions. They don't really fall anywhere, but we haven't talked about them yet, so we really need to. But then after that, we will go ahead and put a wrap on Unit 4 and essentially put a wrap on first semester. All righty. So friends, why don't you guys do me a favor? You know what I'm going to say probably. Why don't you guys go ahead and pause the video and take a chance and take a second here and try these integrals to see what you come up with. All right, so here we go. I see my inside function is a 3x plus 4. So that means du is 3dx. So 1/3 du equals dx. So when I go and I am dealing with my problem here, so do purple for this one. There we go. First of all, I never did change this to a fractional exponent, but by now I'm guessing you guys are probably used to doing that. Still at 0 and 4, because I haven't done my U sub yet. As soon as I do my U substitution, my bounds are going to change. So to figure out what they are, I'm going to plug them into my U function. Let's see what I'm going to deal with. So U of 0 is 3 times 0 plus 4. So that will be 4. So my lower bound of 0 is going to become a lower bound of 4. And U of 4, 3 times 4 plus 4. That's going to end up being 16. So now we can go ahead and finish it from there. And we'll keep everything in terms of U from here on out. So we're going to integrate. So 2/3 U to the 3/2. And when we plug it in, we get 1/3. 2/3 times 16 to the 3/2 minus 2/3 times 4 to the 3 halves. And we can leave it like that if we wanted to. If we don't, we can keep going. We could actually solve it all the way out. So just for the fun of it, I'll go ahead and solve it out here. So 16 to the 3 halves, well, the square root of 16 is 4, so 4/3 would be 64. Times 2 is 128, so 128 over 3. Minus, square root of 4 is 2, 2 cubed is 8, times 2 is 16, so minus 16/3. So I get 1/3. And again, you do not need to simplify on the free response. If it's multiple choice, obviously you would have to. So we get 112 over 3, so 112 over 9. All right, let's try this next one here. So u would be 2 of x plus 1. So that means du equals 2 dx. 1/2 du equals dx. So when we do, oh, almost forgot to do my bounds. I know I'm going to have to do it later, so might as well do it now. So 2 times 0 plus 1. So my lower bound is going to become 1. And my upper bound is going to become 5. So let's do it. First of all, we rewrite because we don't have a quotient rule. So that'd be a -5 now. I almost try to do the derivative of the integral right there. All right, and so we changed our bounds. Instead of 0 and 2, they're going to become 1 and 5. And that is u to the -5 times 1/2 du. So the 1/2 will go out front. At 1 and 5. U to the -5 du. Here we go. So when we do our definite integral, I'm going to add 1 to my exponent, and I'm going to then divide by it. And by the way, something you can do if you want to, you don't have to. You can always bring that -4 out. So I can make that a -1/8. -1/8 right now. If I just don't want to deal with the exponent. So now it's -1/8 times 5 to the -4 minus 1 to the -4. All right, let's try one more. Again, well, I guess we can keep going on this if you want to. So just so you realize this is a positive number here. We get 1 over 625. That's an ugly number. Minus 1. So -624 times -1/8 would be 624 over 8. If you were to simplify it anymore, that's what you'd end up getting. All right, well, let's keep going here, friends. So actually, that goes in evenly. We should keep going. 56 times 8, so it's 7. Oh, 64, 78. Who knew? There you go. All righty. I had to look at that for a second, going, wait a second, that's actually going to work. So u is 4x. Du equals 4 dx. By now, hopefully we're getting really good at these U substitutions. So 1/4 du equals dx. So we plug in our bounds because we're going to figure out what these turn into. So u of 0 is 4 times 0, which is 0. And u times pi over 8 is 4 times pi over 8, which is pi over 2. So change my bounds here real quick to 0 and pi over 2. So now we have our cosine of u times 1/4 du. So these u subs aren't bad when it comes to definite integrals. It just takes a little bit of time. And like I said, we had the time this year, so I thought it'd be better to break this up a little bit, so we're not quite as just overwhelmed by all the material. And we have 1/4 now times integral of cosine would be sine. Zero and pi over 2. And when we plug those numbers in, remember, trig functions we have to evaluate. We're not allowed to leave this as sine of pi over 2 and sine of 0. We always have to go one step further with those guys. So we end up with 1/4 times 1 minus 0. So the entire answer is 1/4. There we go. All right, so there we have definite integrals and U substitution. Let's just go a little bit further here. We're going to talk about even and odd functions. So in case you forgot what an even function is, we're going to go back to pre-calculus for a little bit. Even functions, those are functions where f of x equals negative f of x. I lied. I put the negative in the wrong spot. That's not good. There we are. And the nice thing about these is we've said that they are symmetrical over the y-axis. So some of you guys last year, you judged even and odd based upon symmetry, which isn't necessarily a bad thing, but a lot of times you can't tell. You have to actually evaluate it. Odd functions, these are when we have negative f of x equals f of negative x. And these have rotational symmetry. And it was 180 degrees rotational symmetry. Around the point 0, 0. I guess I probably should have clarified this one. It's a vertical reflection. They were vertically reflected over the x-intercept, over the y-axis. Horizontally reflected. Sorry about that. That's how you can tell if they were even or not. Well, it turns out there's some special little things that kind of come up with integrals and these even and odd functions. First up, if they're even on some closed domain, so let's take an even function. Turns out you don't have to evaluate the entire thing. You only got to actually evaluate it from 0 to a. And we'll see this in an example here in a second. And the function we're going to use that's actually even is going to be just straight old-fashioned x squared. Now, if it's odd, and they are the reciprocals of each other, not reciprocals, the negative of each other. Turns out odd functions, they actually add up to 0. And that idea, we'll see that here in this kind of function, right? Cube root of x. So if we are looking at it and we're trying to figure out why this works, if it's symmetrical over the y-axis, that means this area right here is going to be the same as this area right here, where they're divided by 0, which is, again, why we only got to go from 0 to that letter out. If it is rotational symmetry, so let's take a look at what this one looks like. Cube root function is going to kind of come up here, but notice on the other side it goes down. So all the positive area or positive displacement from 0 to a, it would have the same negative amount that would be below it. And when you add up those things, they're additive inverses of each other, therefore they're going to equal 0. So let's see how this works for these two functions. So 0, oh, I lied. Let's see how these would actually work for these two functions, for even and odd. If I were to go normally and integrate this, I'd get x cubed over 3. And friends, you don't necessarily need to determine whether functions are even or odd. It's more of, if it pops up, you need to have just a basic understanding of what's going on and what happens if they actually are even or odd. So we have 2 cubed over 3 minus a negative 2 cubed over 3. And we end up with 8/3 plus 8/3. Which is 16/3. So now let's see what that would have looked like if we would have done the definition for even. If that little property holds true. So according to that little theorem, that little property, I only needed to take it from 0 to 2 and multiply the answer by 2. And right now you guys should probably be able to see kind of like, well, these, you actually are going to end up with 2 of those, so it should work. So 2 times the whole thing from x cubed over 3 from 0 to 2. So 2 times 8/3 minus 0, and you end up with 16/3. Just a little illustration about how that works with even functions. Let's see how it might work with odd functions then. Let's go from -8 to 8. So if I do my cube root of x, by now, again, you know that I am not going to do a cube root. We're making that a fractional exponent. So 3/4 times x to the 4/3 from -8 to 8. So 3/4. When I plug it all in there, you get 8 to the 4/3. There we go. Minus 3/4 times -8 to the 4/3. So when you do the cube root of 8, it's 2, but 2 to the 4th power is 16. So I get 3/4 times 16. Minus -8, cube root of that is -2, but -2 to the 4th power is, always makes it go positive. So that'd be 16. And lo and behold, the odd function does actually have an area or displacement of 0. So if I can recognize that's an odd function, if I know that's an odd function to begin with, and I'm asked to integrate it, no sense dealing with actually integrating it. If it's odd, then I know it's going to end up being equal to 0. Assuming, again, notice, assuming the lower and upper bounds are the same. Evens, this assumes the lower and the upper bounds are the same, just one's positive, one's negative. All righty, friends. Well, that takes care of chapter 4 and takes care of first semester. So look forward to seeing you in class. We'll talk more about it.